Good evening, everyone. I'll be your TA for the course Fundamentals of Electronic Device Fabrication, and this will be our first live session so far. And has anyone gone through the contents of week 0 PPT or anything? Like, I could I see some answers like whether you have gone through what is expected in these live sessions, or what are your expectations? Anything, if anybody has any opinion, you can come up, or I'll just brief you through it. So, in these live sessions, it is expected that we will be practicing some questions, and at the same time, we will be having doubt clearing sessions. And you can post your questions to me, and at the same time, you can post your questions personally to me to my email. You can post the questions in the discussion forum. And I think now I can present my screen and we can start the discussion. So, I hope the PPT is visible to all of you. Can anybody unmute and confirm? Yes. Okay, thank you, thank you. So this is the first live tutorial on the course Fundamentals of Electronic Device Fabrication. I am Santara Krishnan P. I am a PMR fellow from Indian Institute of Technology, Madras, and these live sessions are brought to you in association with NPTEL and PMRF TA-ship. So feel free to ask your questions. Don't feel that these questions are very like irrelevant or they're very tough. Just be confident and ask your question, come up with your doubts, and please go through the lectures regularly every week. And this course is actually a continuation to another course by Professor Parsuram and Swaminathan, that is Fundamentals of Electronic Materials and Devices. And in case you want to have the fundamentals of semiconductor materials, so I would suggest that in your free time you can go through that lectures as well. So please be ready with your questions. Today we'll be practicing a few sample questions. We'll be seeing those questions one by one. And I believe these questions will be helpful to you in doing your assignments and at the same time for your final examination. I think the course registration has already ended on 1st August. You'll be able to register for the examination from 15th of this month, starting until the end of this month. And your first and second assignments are due by next week. So please do that regularly as well. So now let us start the session. So first we'll go through a quick recap of what is in week 1. So if you have gone through the contents of week 1, you might have noticed that we have gone through introduction and overview of semiconductor device fabrication. We started with IC in history. That is, we saw the different levels of integration, how this has progressed along the centuries. We saw Moore's law, the diodes and triodes, and what has been their precursors and what will be their successors. And then we saw an overview of IC fabrication. Sorry, I have somebody waiting, I guess. Okay. So then we saw an overview of IC fabrication. We saw submerged arc electrode processes, Siemens process, Chukralski and float zone. And then we went on to wafer slicing, wafer fabrication, etc. Wafer fabrication part will be discussed in detail during the next weeks. And then we saw the basics of layering, doping, patterning, heat treatment, and a few examples where we saw how an NPN transistor is manufactured. I hope all of you have already gone through those material. So again, I suggest that all of you please join on time so that I don't have to pause my video in between and keep admitting you all. So now we'll see a few practice questions. Okay. So starting, the first electronic amplifier, a precursor to the modern day transistor is, your options are radio, diode, IC circuit, that is an integrated circuit, or a triode. So I request any of you to just unmute and can come up with few answers. That would be good. I'm not hearing any answers. So please. No, the first electronic amplifier, a precursor, that is, today we have modern day transistors, right? So before finding the transistor, there was some other device. So what is common between these options and a transistor? A transistor is a three-terminal device. So which of these options is a three-terminal device? You can think in that way. Yeah, sure. That is the answer. So triode has three terminals, that is an anode, cathode, and a grid, which is similar to a modern day transistor. with source, drain, and grate. And somebody has left the meeting actually. So, okay. So the next question is the Siemens process converts silica to MgS, MgS to EgS, EgS to single crystal ingot, MgS to single crystal ingot. So if anybody has the answer, you can please unmute and speak. Yeah. So wait 1 second. I'm just presenting again. No, the Siemens process. Silica to MgS, what was the process? Silica to MgS we used to do by reducing silica, that is sand with coke, right? That has another name. It is not Siemens process. Any other answers? It's okay. You can come up with your answers. You can explain. It's fine. Like we can have an interactive session. The answer need not be right. Any answers? No. MGS to EGS. Yeah, that's the answer. Thank you. So that is the answer. So Siemens process converts MGS to EGS. So I'll just revise the entire process. Submerged arc electrode process is used for converting silica to MGS. That is, we will be reducing SiO2 with coke or carbon to get metallurgical grade silicon. That is submerged arc electrode process. And then from metallurgical grade silicon, which is 98% pure, we will be converting it into electronic grade silicon, which is 99.79, that much purity it will be having. And that particular process, after Siemens process, we will be getting a polycrystalline ingot. This polycrystalline ingot has to be converted into a single crystal ingot. And this is achieved through two different processes, that is Czochralski and float zone. So if anybody of you has revised Czochralski or float zone, can you just like one of you can talk about Czochralski and one of you can talk about float zone processes, if you know. Anybody? Your voice is very feeble. Can you talk a bit louder? Yeah, yeah, it's fine. It's fine. It's fine. Yeah, yeah, yeah. Yeah, so one more point is there for converting it into a single crystal, and the single crystal will be having particular orientation, right? Like 100, 111. To get that particular orientation, we'll keep a seed crystal. So inside the molten metal, we'll be keeping a seed crystal and we'll be rotating it and pulling outside. And as you said, it will become a single crystal ingot. So that is the way. So anybody knows? Thank you. What was your name? Yeah, thank you, Sanasi. So anybody else? Float zone process? Okay, so I'll explain myself. So Czochralski, we already know we will be keeping a seed crystal inside the melt, and from the melt we will be rotating and solidifying it. In float zone process, what we do is that we will be having the polycrystal ingot, right? We will be heating the polycrystal ingot in contact with the seed crystal. So while heating, this polycrystal will be converted into single crystal, and we'll along the road we will be getting single crystal ingot. And this single crystal ingot will then be sliced into thin wafers that is used for the IC manufacturing. So I hope we can move on to the next question. So, which of the following is an example of heat treatment process? So, during the wafer fabrication, there are many like steps, right? Layering is there, patterning is there, doping is there, contact placing is there, heat treatment is there. So, which of these options is a heat treatment process? So, your options are ion implantation of dopants, silicide formation after metal deposition, spin coating of the photoresist, electroplating of metal interconnects. Anybody has the answer to this question? I think like many of you not have might have not still watched the videos. Is that right? Like it's nothing to worry. You can watch the videos according to your wish, and it's just that you should complete it systematically and come up with questions. Then only I'll be able to help you. So please do watch the video systematically. So which of the following is an example of a heat treatment process? Like randomly you can shoot your answers. It's fine. It need not be correct. Anybody? Not visible in the sense? Is it the same for everyone or only for you? Is it visible to others? Okay. So it might be an issue with the connection or something. Let me check. Is it visible now? Yeah. Which of the following is an example of heat treatment process? Iron implantation of dopants, silicide formation after metal deposition, spin coating of the photoresist, electroplating of metal interconnects. Any answers? No, it's not. Other answers? Uh, food. No. Anyone else? That also is not correct. So the final option is silicide formation after metal deposition. So I'll explain how. So basically, the thing is, in wafer fabrication, there will be different processes, right? So first one is layering. We will be having a P-type or N-type wafer, and we will be depositing an oxide layer on top of it. That is layering process. And after this layering process, we will do patterning. We will use photoresist, and this photoresist will create regions that are active to light, and using that, we will be able to create specific patterns on the wafer. And once that has been done, like we can use to dope the wafer from the beginning, or we can do doping later on also by layering. So after all these processes are done, for using it, we need to keep metal contacts, right? Something should be there to contact the circuit, right? So for that, we need metal deposition. So how is that particular process achieved? So that is by heat treatment. First, what we will be doing, there is a silicon wafer and we will deposit a metal on top of it. And while heating, a chemical reaction will take place between the metal and the silicon wafer, and a silicide will be formed. This is how the circuit becomes conducting. So is it clear? Yeah. So next question is, a wafer has two flats that are 90-degree to each other. This type of wafer is. It's a quite straightforward question. Sorry? Yeah, it's correct. P of 100 is correct. It's correct. Yeah, I have to admit somebody else. Everybody, next time onwards, try to please be on time. Yeah. So P of 100 is the right answer. So from here we can see if there is only a primary flat, it is P type 111. If there is a primary flat and a secondary flat at 45-degree, it is N type 111. And if there are two flats at 90-degree to each other, it is a P type 100. And if there are two primary and secondary flat and both are at 180 degrees, it is an N type 100. So these kinds of questions you can expect for your assignment as well as your end exam. So please be prepared for such kind of questions. So the next question is, the first step in IC manufacturing is, so wafer fabrication and sorting, single crystal growth, packaging, converting sand to MGS. Which will be? Yeah, that is the correct answer. So here you can say first is the material preparation step. We'll be converting sand to MgS. Then we have a polycrystalline ingot. The polycrystalline ingot will be converted into a single crystal ingot. And then we will be doing wafer fabrication and sorting. And in wafer fabrication, we have layering, patterning, doping, heat treatment, etc. Finally, we will be doing packaging and then electrical testing. So that's the correct answer, converting sand to Mgs. So the next question is, sorry, portion of a wafer that is a standalone unit is called A, die, B, scribe line, C, edge die, and D, test chip. Yeah, the correct answer is die. So if we are taking a wafer like this, so a standalone unit, that is, which is the area of the wafer that is functional, which acts as a gate or a switch or whatever, or it's part of a functional part of an IC stem, as a chip. And in between, we will be having small regions called test die. It is used for the electrical testing to find out whether the wafer is working or not. And to separate the different dies, we will be having scribe lines. So these are the scribe lines that you can see on a particular wafer. These scribe lines can be blank. One thing is they cannot have any functionality, or another option is they might be having special patterns on them required for testing. And finally, we will be having edge chips, that is incomplete dies along the edges. These are not functional. So can anyone tell me why wafers are always round instead of having some another shape like square or yeah. So one thing is that during the process like Czochralski and float zone, we will be getting a crystal wafer that is spherical. And the other thing is that if a wafer, like these are very thin wafers, right, it will be like very very thin. So if it is having sharp edges, there will be possibility of stress concentration, and while handling there is a large possibility that it will break. So people who have used like silicon wafers here might understand how fragile these things are. So to avoid this also, they will be having rounded edges. So the next question is, device miniaturization is depend on which of the following steps? Layering, doping, patterning, heat treatment. So all of these options are part of the wafer fabrication process. So which of them is responsible for device miniaturization? We know that each year IC is start becoming small, go on becoming smaller, and the number of transistors on them becomes increasing. So which process is responsible for that? No? Yeah. Option C, patterning is the answer. So, can anybody tell me what is patterning first? Anybody? Yeah. Yes. Yeah. Yeah, so like functionalizing an IC is done by patterning basically. So how small we can make a particular pattern, that is how small your functional units on an IC can be. So during patterning, first we will be depositing an oxide layer, and then we will be keeping a pattern that is actually a copy of the circuit that we want. Then we will apply a photoresist and then irradiate it with light, and whatever happens, and the portion covering the photoresist won't be functionalized, the rest regions will be functionalized. And that is how we actually make different gates or sources or drains in an IC. So that is the patterning step. And the complexer we can make a particular pattern, the more smaller the device will become. So that is how device becomes smaller and transistors on them goes on increasing. So there is one particular law that states the number of transistors on an IC doubles every 2 years. So can anybody tell me what that law is? Yeah, yeah, Moore's law. Okay. So that everyone knows, I guess. So the next question is, lateral spread is minimum for dash doping technique. So before that, like tell me what are the two different doping techniques first. Yeah. So can anybody explain what is thermal diffusion and what is ion implantation? Anybody? Okay. Okay, so two techniques of doping, as she said, is thermal diffusion and ion implantation. And lateral spread will be minimum for ion implantation. So I'll just brief you on both techniques. So in case of thermal diffusion, we will be keeping the dopant on top of the wafer, and by providing a temperature gradient, we will be driving it into the material. So concentration will be maximum on the surface, and as we go down into the wafer, this concentration will go on reducing, and as it goes down there will be spreading of the dopants also. There is not much control that we can exercise on this particular process. But ion implantation, on the other hand, high energy ions will be embedded into the wafer, so the concentration won't be maximum on top, it will be maximum at a particular depth from the top. So that is ion implantation technique. So is it clear for everyone? Yeah. So the next question is, deep trenches with high aspect ratios are effectively coated by. So while device fabrication, we know that there is layering, doping, patterning, heat treatment, right? So during the layering process, we might have seen, like those who have noticed on wafers, there will be structures like this. These are actually transistors grade. There will be rectangular structures, and some of them will be very tiny, but their length will be long. That is what is meant by deep trenches. That is, they will be having high aspect ratio, that is width to length will be very high. So which method can be used for coating such trenches? No, like there are different coating techniques, like, right? So what do you use for growing oxide layers on a material, like leave about the IC part, like normally on materials, with by which method will you grow film on them? So you can think in that way. Yeah, that is grown layers. Yet another deposition method, if any, you can say, like very complicated deposition method. Yeah, so which among these deep trenches will be coated using physical or chemical? Yeah, that is right. So deep trenches with high aspect ratios are effectively coated by CVD, that is chemical vapor deposition. So can anybody who knows chemical vapor deposition, can you just speak up if anybody knows chemical vapor deposition? Anybody? Okay, so in chemical vapor deposition, we will be heating the substance and it will be vaporized, and these vapors will go on and then form a chemical reaction with the substrate, right? And it is a highly controllable process, and we can atom by atom impinge it onto the substrate so that we can have a line by line deposition. So that is how very deep trenches with high aspect ratios are coated in case of integrated circuits. So current levels of device integration is called, so different levels of device integration is there, right? Like VLSI, MLSI, and so on. So current levels of device integration is, no, it's more than VLSI. So what would you call it? Yeah. So ULSI is the answer. So in case of so different levels of integration. So how many number of components do you know is there in ULSI? Number of components per chip. Can you make a guess? Huh? Yes. Above 10 power 6 components will be there. That's approximately 1 million, right? Yeah. So in small scale integration, there will be tens per chip. In medium, there will be thousands per chip. Large scale means it will be in the range of 10 power 5. Very large, 10 power 5 to 10 power 6. And ultra large scale means that there will be more than 10 power 6 components per chip. So somebody else has requested to join. So Which of the following is an example of a process to produce grown layers? So we have already discussed, right? PVD, CVD, all these things. And out of this, there are two types of layers. There are grown layers and deposited layers. So among these four options, that is MBE, that is molecular beam epitaxy, sputtering, evaporation, and oxidation. Which of the following is an example to produce grown layers? So what will be the answer? Yes, oxidation is the answer. So, layering operations can be done in two ways. We can produce grown layers or deposited layers. Grown layers are produced by oxidation or nitridation, and deposited layers can be produced by chemical vapor deposition, evaporation, sputtering, and electroplating. So, in our case, to produce grown layers, the options that matches oxidation. Okay, I hope it's clear for everyone. So next question is, why is float zone technique harder to implement for larger wafers? Like there is, we are converting polycrystalline electronic grade silicon to single crystal electronic grade silicon, right? So there are two methods, Czochralski and float zone, and one is float zone. So float zone cannot be used for large wafers. What is the reason? Anybody? Like we have already said, right, in Czochralski, there will be the melted pool of electronic grade, like molten metallurgical grade silicon will be there. We will be keeping the seed of the required orientation. We will pull the seed up slowly by rotating, and we will get the single crystalline ingot. That is Czochralski part. In float zone, the polycrystalline ingot will be as such, and using an external heating source, we will be like directionally heating it, and the seed will be in contact with the polycrystalline ingot, and one by one we will be go on heating the rod, and this particular region that is being heated, it will melt, it is resolidified again, and that is how we get the solidified single crystal ingot, right? So why is float zone technique harder for larger wafers? So in Czochralski, it is getting solidified from the pool, but in float zone, the road is just changing its nature. Nothing is being fully melted and solidified. So what will be the reason? What happens when we are having different levels of solidification in different regions? Anybody? Like people might have heard of anything like directional solidification, solidification stresses, etc. Has anyone heard of those terms? Anybody? Okay, I think none of you have heard of those. See, so float zone technique involves the melting of a portion of the poly ingot and then solidifying. For larger wafers, uniform melting won't be possible, and the difference in rate of solidification produces stresses and defects. That is the reason why float zone technique cannot be used for larger wafers. So, is that clear for everyone? Yeah. So any doubt for Czochralski and float zone, if anybody has, you can ask now, so we can clarify and go forward. Or any doubt from whatever is discussed so far, we can clarify fully. Flat. Yeah. Okay. Flats part means two flat means. Yeah. Yeah. Only one flat means that will be that particular type you are using might be that it is P type and 111. Like whenever you're using an n type or a different plane, say this is like a single crystal, right? And each single crystal will be having one particular orientation, and that is given by these indices. That is 111. So one flat only means that your material is P type and it is 111 orientation. Yeah, yeah. Anybody else? I think somebody has written in something in the chat box. So this is like a live session. You can actually ask your doubts. That would be better, I guess. Like the person who posted, can you please unmute and speak? Nobody's responding. I guess nobody has any more questions then. Okay, so we'll move on. So next question is, write down the equations converting silica into Mgs and Egs. So I would like to like give you 2 minutes. All of you can take a piece of paper and try writing it down, and then we'll compare your answers with the correct answer. So once you're finished, you can tell the answers also. Like converting silica to MgS. So silica means we will be having SiO2 as starting, and we know it is the submerged start process. So we will be heating it with carbon. So what happens when we heat silica with carbon? That is first part, and then we will be having silicon. We'll be converting it into EGS, right? That is the Siemens process. So you can try writing the equations down. Like these questions will be like mostly be there in your assignments and your end exams. So if you're planning yourself to write the NPTEL exams, I suggest that you go through these equations thoroughly. So you can start trying in like 1 or 2 minutes. I'll take your answers. From there we'll go. Like, is the presentation visible to all of you? And am I audible? Can anybody please confirm? Yeah. So, have you started finding out what happens while converting silica to MgS and MgS to EGS? So first is submerged arc electrode process, second is Siemens process. So you have to write the equations for both these processes. So shall I start, or is everybody still trying? So can I give the answers now, or should you need a little more time? Yeah, these are from the syllabus itself. Yeah, it is the fundamentals of electronic device fabrication, and all of this is discussed in the first week contents itself. Okay, fine, fine, fine. So don't worry if you're not started. And once you start going through the videos, whatever doubts you have, please note it down so that next time you join, we can discuss those also. Okay. Yeah, yeah, it's fine. It's fine. You can like come up with your questions next week, or you can email me if you have any doubt. The both are fine. Yeah, sure. Yeah, yeah. Like I'll be posting soon. I'll post it. Yeah. So rest of the people, anybody got the equations? Okay, I think I'll show the answers. So first one is silica into MgS, right? That is the submerged dark electrode process. We will be taking sand, that is SiO2. It will be reacted with coke, that is carbon, to produce silicon carbide. And this silicon carbide will react with rest of the silica, that is SiO2 sand, to form silicon. And this takes place inside a furnace. So the reaction will be as silicon carbide, which is in solid form, reacts with SiO2 in the solid form, that is sand, to give silicon, that is molten silicon, and silicon oxide in gaseous, and carbon monoxide, that is in the gaseous form. So this is the submerged dark electrode process, and it is the first step in converting silica into MgS. So next is Mgs to Egs. So MgS is the metallurgical grade silicon. It is 98% pure, and it is used for producing metallurgical alloys and other purposes. But this cannot be used for producing electronic circuits, right? So we need more purity. So we'll be converting it into electronic grade silicon. This electronic grade silicon is 99.79 pure. So that is known as the 9 nines purity. And this particular process is called Siemens process, and it is carried out in a fluidized bed reactor. This is actually a fractional distillation process. So silicon in the solid form will be reacted with hydrochloric acid in the gaseous forms, and we will get tetrachlorosilane in the gaseous form. And this tetrachlorosilane is again reacted with hydrogen, and this process will be repeated multiple times to get electronic grade silicon and HCl. So that is the process. Somebody else has posted something, I think. Like since I'm recording, I'm not able to get what you're posting in the message window. So if everybody can just speak up with their doubts, that would be better. So are these two sets of equations clear for everyone? Yeah. So I hope these two processes are clear. That is the submerged arc electrode process and the Siemens process. So these are the questions that we'll be discussing today. Like since this is the first session, I have brought up with only a few questions. Now you might have got an idea of how the sessions, like continuing three sessions will be. And if there is any requirement, we can keep additional sessions also. And for the assignments as well as the end part exam, you will be having multiple choice questions, but these kinds of equations can also be asked in multiple choice. I think therefore you should be familiar with the entire content that is posted in NPTEL. So I have a few questions that is not from related to this syllabus only, but that is from a more general perspective point of view. So if you have gone through week one contents, towards the end of the contents there is an example of how an NPN transistor is created. So when you come for the next week, please do answer question number 14 and 15. So the first question is, starting from a blank N-type silicon wafer, show all the steps that are required to create a simple PN junction where electrical contacts for both P-type and N-type should be at the top. So now this question might seem a bit confusing, but if you go through the last lecture from last week, like it is clearly mentioned. So in a similar manner, you can start like basically you have to answer like first layering will be done with so and so material, then patterning will be done, then heat treatment will be done. See, heat treatment comes in the electrical contacts part, and that is basically last. Since P and N it should be on the top, that will be basically last. So like that you have to get a series of steps, and if you're comfortable with the steps, there is also a way where you can picturize, you can draw the whole thing, how the IC is manufactured, so that you can answer for next week. So next is question number 15. Predict the breakdown of Moore's law and justify. So Moore's law, as we have already said, it was predicted that every 2 years the number of transistors on an IC will double. But it cannot go on indefinitely, right? At some point of time, the number of transistors will be so much so that it cannot be embedded into a one particular IC. So when will this particular Moore's law break down? So now we are in the year 2022. So just predict according to your conscience when this will break down and bring up with your justification. So why it won't work, this particular law won't work beyond a particular period of time. So that is all for today's session. So if anybody has any kind of doubts related to the process or related to this particular contents, now you can ask. Like related to the examination, or what will be the further contents, or how you can get help with basic understanding of semiconductor materials. Any doubts if you have, you can ask right now. Feel free to ask. I am also a student like you, so like we can interact freely, it's fine. So please come up with your questions. Yeah. Okay, like exam registration has not started, right? Exam registration, I think it was mentioned to us that it will start from 15th of this month. Yeah, like, and yeah, like now it is time for enrollment, and later you have to apply for the exam. And while applying for the exam, you will be given some 2 weeks time. And if initially if you face any problem, please directly email to NPTL so they can personally clarify your issue. Yeah, once the date starts, you can register for the examination. Now they might have not opened the portal, that's why. Yeah. Yeah. And there is one more course, as I mentioned, like fundamentals of electronic materials. So this is the fabrication part of devices, right? So in order to get into that, first we need to know the basics of semiconductors. That would be good if you're planning to work in semiconductor material. So I suggest that it is freely available on YouTube. You can visit those lectures also, like P-type materials, N-type materials, dopants, and basic problems related to those, then PN junctions, a bit of solar, a bit of optics, everything will be covered in that particular course. So in your free time, whatever portions you find difficult, you can visit those lectures as well. So anything else? In YouTube, you can find the lectures. Yeah, the professor's name is Parashuraman Swaminathan, and he has lectures on electronic materials, like very extensive lectures on electronic materials you can find in his YouTube channel. Yeah. And if you want to take it as a course, like now, fundamentals of electronic device fabrication is offered. Later on, that course will also be offered in NPTL. So you can enroll during that time also. Either is fine. Yeah. So I think that's all for this week. Anybody with any questions? Yeah, sure, sure, sure. Yeah, yeah. For the exam. Format of the exam will be multiple choice exam. So number of questions, I think I'll get back to you with that questions. I've never taken an NPTL course or an exam. So next week I'll inform like number of questions and what will be the duration, etc. Yeah, yeah. Yeah, yeah, it will be uploaded in the NPTL portal. It will be there. And there will be a link to a YouTube channel also, and you will find the videos also there. Both will be given to you, no worries. Yeah. Yeah, like, or you can, like, there is the NPTL site, right? In the NPTL site where you enrolled, you can find all these. Link to today's video, link to materials, everything will be there. Yeah, yeah, it will be there on your Swayam portal. Yeah, yeah. Like maybe just it is the starting week, that is why they might have not posted. And once this session is over, and once I upload the link to them, they will post it on the Swayam portal. Yeah. Yeah, surely. Yeah, like, yeah, it will be available to you. And if you are in any kind of urgent need, I can like mail it to you or so. But I think NPTL will do it first. So let me see that. Yeah. Like anyway, these PPT and these videos will be made available to you. And you can visit the YouTube channel also. From there also, you can get these questions. Like same lectures, video recorded once, we will be uploading there. Was that helpful? Yeah, thank you. Yeah, so thank you for your attention. So please post your questions on email to me, and also please post your additional questions in the discussion forum. There are other teaching assistants also, so that we can like answer those questions over there, or we can discuss with the prof and then put the answers up. So feel free to ask, and please go through the lecture systematically to avoid a last minute rush. Do your assignments correctly, and next week there is a deadline. Please do your assignments before that. So feel free to ask all sorts of questions while doing the lectures. Please note down your questions. And if more people feel that a particular topic is hard, we can keep a short session for explaining that particular concept alone. So that also can be done. So that's all about today. Thank you everybody for your time. So we'll meet next week, same link on Tuesday from 6 p.m. to 7 p.m. And whatever suggestions you have, also that also you can email me whether I should include a particular topic or more questions. Like since this is a conceptual based syllabus, we will be doing more of concept questions. And wherever numericals are there, I will include numericals also. So feel free to contact me in my email ID, that is santra.pmrfiatm@gmail.com. So I hope the session was helpful to all of you. Thank you. And now you can leave the meeting. Thank you so much. Thank you. Bye bye.